Yeah, hello everyone. Today we are going to study about longitudinal static stability. Before going to this, what is stability? First, what is stability? What is stability? Stability is nothing but response of a body or of an object to the disturbance from its equilibrium position. That is called stability. If I am trying to disturb a body, if I am trying to disturb an object from its equilibrium position, how it will respond? That response is nothing but stability. For example, take a curved surface. Okay, take a curved surface. Consider a ball at the middle of this curved plate. Now if I try to disturb this ball, means if I take this ball and keep it here, this is called equilibrium position. If I keep it here and I leave this, what happened? Again it will come back to its original position. Am I right? Again it will come back to its original position. Or just assume, if I put a small force here, if I apply a small force here, and it will displace this ball from this position to this position. After what happens? Again it will come back to its original position. So this is stability. Stability means, or consider one more plate like this. This is also curved plate. Now this is the equilibrium position, sir. If I apply a small force, or if I give a small displacement to this ball, what happens? It will go away from the equilibrium position. It will never come back to its equilibrium position. Am I right? It will go away from this equilibrium position. So the response of a body or of an object to the disturbance from its equilibrium position, that is called stability. In this case, if it is having a tendency to come back to its equilibrium position, here I am giving a small displacement to this ball. After it gets disturbed, it's able to come back to its original position. So this condition is called stable. This is stable condition. Here what happens? If I give a small disturbance to this ball, what happens? It will not come back to its original position. It will go away from this equilibrium position. This condition is called unstable. Okay, stability is nothing but response of an aircraft or response of a body or any body to the disturbance. So if it tends to come back to its original position, that is stable condition. If it tends to go away from the equilibrium position, that is called unstable condition. Okay, here also in aircraft also same thing happen. Consider aircraft. Okay, consider aircraft. It's moving like this. Okay, now because of some disturbance, just assume that there is an increase in angle of attack. Now an aircraft, it will be like this. Because of this disturbance, there is an increase in angle of attack delta alpha. Now if this aircraft tries to come back to its original position, if it tends to come back to its original position, this is called stable. If it tends to go away from this equilibrium position like this, then this is unstable condition. Am I right? This is unstable condition. Or if it tends to continue with the new position only, it will not come back to its original position. It will not go away. Sorry, it will not go away from this new position. It will not come back to its original position, but just it is moving like this only. Once it get disturbed, there is an increase in delta alpha because of this disturbance. Again it tries to move in this position only. Now this is called neutrally stable. This is neutrally stable. This is stable, this is unstable, this is neutrally stable. If a body tends to come back to its original position, that is stable. If body tends to go away from the equilibrium position, that is unstable. If a body continues to move in a new position, in a disturbed position, then it is neutrally stable. That's it. This is all about this stability. This is basic, you should know this. Okay, what is stability means. Now before going to the derivation, in stability one is two types. Static stability, you know what is stability? Static stability and second one is dynamic stability. Dynamic stability. What is the static stability? Static stability means the very first reaction of the aircraft to the disturbance. That is called static stability. Dynamic stability, here we are dealing with the time, over a period of time, what is the response of an aircraft. For example, consider a spring mass system. This is the spring, this is mass m. Okay, if I give a small displacement x, what happens? If I give a small displacement like this, okay, just like this is the actual body m. Here, after giving displacement, this body will come here, m. Okay, just assume that this is the distance x. After giving this displacement, what happened? There is a restoring force will be generated in this spring. This restoring force, what it will do? It will pull the body back. Am I right? It will pull this mass back. So what is the very first reaction after giving this displacement? It tends to the initial tendency of a body to come back to its original position. The initial tendency, the very first reaction, it will go back to it. What it will do? It will try to go back to its original position. The very first reaction is called static stability. Am I right? Static stability. It will pull the body. The velocity increases. This is called static stability. Just assume that once it pulls the body, what happens? The velocity increases. The velocity of this mass increases. This is the equilibrium position. Till here, this whatever this elastic force, it keeps pulling this mass till it comes back to its original position. Means the velocity keeps increases at each and every point till it reaches its equilibrium position. The velocity keeps increases means when it comes to its original position, it's having the maximum velocity. Am I right? I am disturbing it. I displace this body by displacement given x. Means, how can I say that? If I give a small displacement x at this position, if I leave like this, after I leave this, what happens? This elastic force tries to pull this. If it is pulling, means there is a force acts on this mass m at each and every point. Means it keeps pulling this body. If it keep pulling this body, each and every point, of course, force is equal to mass into acceleration. There is a force. So acceleration, the velocity keeps increases. If velocity keeps increases, at this point when it reaches its equilibrium position, there is a v maximum velocity will be there. It will attain the maximum velocity. So even though if it reaches its equilibrium position, the velocity will be high. Means there is a momentum, mass into velocity. There is a high momentum. When it is having the high momentum, what happens? It will not stop here because it is having the maximum velocity. So it will move in the opposite direction again, like this, in this direction. Again it will come. Means what is the response? Initial displacement x. I will give this displacement. So what is the very first reaction at this point? It will try to pull this towards the equilibrium position. This is the very first reaction. This is called static stability at this point. When I give the displacement, the very first reaction is called static stability. Static stability. It will reach its equilibrium position. At this point, it reaches maximum velocity. So it's having a high moment, maximum moment. What happens? It moves in the opposite direction. It's having a moment. Again, it will come like this. This is the condition. These things we have studied in structures. Am I right? Vibration. These things we have studied in vibration. So over a period of time, this is the response of an aircraft. This is the response of a body. This is the response of this mass m. So over a period of time, what is this response? So this is called dynamic stability. What is the first response when I give the disturbance? That is static stability. That's it. The difference is static stability, the very first reaction. What's dynamic stability? Over a period of time, I'm going to take this response of an aircraft, a response of any body. Here also same thing happens. Even in aircraft also same thing happens. What happens in aircraft? Same thing. Just assume that, just consider this as an aircraft. After it is disturbed, if I give a, there is an increase in angle of attack alpha, because of some disturbance there is an increase in angle of attack, what happens? There is a nose down moment will be generated. It tries to come back to its original position. The first reaction, the initial tendency of an aircraft to come back to its original position, that is called statically stable. But each and every time there is angular momentum, am I right? Because initially at this point, this is the condition at which CmCg equals to 0, means this is trimmed condition. Here there is no momentum, equilibrium position, just it's moving like this. Because of some disturbance, now there is a momentum generated, there is an increase in angle of attack. If there is an increase in angle of attack, there is a change in force that is generated due to lifting surfaces. Because of this force, the restoring moment will be generated. It might be a restoring moment or destabilizing moment, whatever it may be. I am taking it as a restoring moment will be generated because of disturbance. So the moment increase, the very first reaction is it will try to come back to its original position, that is statically stable, and each and every point there is a restoring force. What it will, there is a restoring moment. This moment tries to create, there is a maximum angular moment at this point. The angular moment increases at each and every point. When it comes back, when it comes to its equilibrium position, there is a maximum angular moment, so it move away from the equilibrium position. Again it will come back like this only, same response. Am I right? Come back to its original position, there is a maximum angular moment. Again it will move like this, it's try to move like this. Again it will come back like this. This is called, this is undamped condition. I am talking about undamped conditions. Undamped means there is no damper, there is no resistance to the motion, there is no dissipation in energy, all are same. These things we studied in vibration. This just I am telling. Okay, what is dynamic stability, what is static stability, understand? Now we are going to study on aircraft. Actually this is what we need to study. Okay, now consider an aerofoil. Consider an aerofoil, just assume that it is symmetric or whatever it may be. Consider an aerofoil. Now this, consider an AC point here. What is AC? Aerodynamic center. Consider CG. What is CG? Center of gravity. What is AC? Aerodynamic center. Aerodynamic center, what is the point? This is the point at which the pitching moment is independent of the angle of attack. Am I right? Is independent of the angle of attack, means if you change the angle of attack also, the moment at this point, pitching moment at this point will not change, it remains constant. That is called aerodynamic center. What is center of gravity? Where whole weight of the aircraft is assumed to be concentrated, that is called center of gravity. But here I am considering only aerofoil or only wing. Take it as a wing. This is the center of gravity of the wing. Okay, this is the center of gravity of the wing, this is the aerodynamic center of this wing. Now if there is a disturbance, there is a change in angle of attack. Okay, just assume that this is the aerodynamic center. If there is a change in angle of attack due to some disturbance, what happens here? Due to disturbance, the lift will be increased. As angle of attack increased, lift will be increased. As lift will be increased, what is the moment generated here? What is the moment generated here? Of course, this is the CG point. We are always taking the moment about the CG point, because any body, it tries to, in a space, it tries to rotate or move about the CG point, center of gravity. So this is the CG. I am assuming that all weight is assumed to be concentrated here. Now if there is a change in angle of attack, there is a change in increase in angle of attack because of some disturbance, the lift will also be increased. As lift will be increased, what happened? It will create nose down moment, means for nose up disturbance, it will generate the nose down moment, means this is stable. Am I right? This is stable. Here dCm by d alpha is less than 0, means what does it mean? As the angle of attack increases, moment decreases. Am I right? As this is the negative slope, slope should be like this. If you take This is the negative slope. If you write like this, this is positive slope. What does it mean? If you take and y and x, mathematics, simple mathematics. If you increase the x, y also increases. Here, if you increase the x, y decreases. This is negative slope, this is positive slope. Here also, if you increase the alpha, moment decreases. Got it? So this is the point. If you see, this is the condition, case 1. Now consider case 2. Same aerofoil. Consider it as a symmetric. This one also symmetric or cambered airfoil. Consider this as a symmetric airfoil. Consider the symmetric. This is also symmetric airfoil. But here I am placing the AC point here, CG point here, means I am placing CG point behind my AC point. Okay, now if there is an increase in angle of attack, what happens now? There is an increase in angle of attack. Lift increases. Initially there is a lift L, now L plus delta L, because of this delta alpha. There is a change in angle of attack, delta alpha. There is an increase in angle of attack, delta alpha. Because of delta alpha, lift also increases. As lift increases, what happens? The moment also increases. This is the moment. This is the CG point. What is the moment? Like this. Like this. Means for a nose up disturbance, here nose up moment will be generated. Am I right? Nose up moment will be generated, means what does it mean? It's going away from the equilibrium position. It will not come back to its original position. So this is statically unstable. This is statically stable. This is statically unstable. That's it. For any lifting surface, if the CG point is forward to my AC point, then that is statically stable. For any lifting surface, if the CG point is behind my AC point, that is statically unstable. This is what I am trying to say. Okay, even though if you consider the cambered aerofoil also same thing. Just assume that cambered aerofoil, CG point here, AC point here, same thing. There is an increase in angle of attack, there is a decrease in angle, there is an increase in angle of attack. The lift increases, then this lift increases, it will create for nose up moment, for nose up disturbance, it will create the nose down moment. Same thing. Okay, but what is the sign convention we are doing? For pitch up moment, means for nose up moment will take positive. For nose down moment, means nose down, this moment is negative, this moment is positive. Nose down moment is negative. Understand? These are the basics actually. These are the basics. Before going to solve the equation, before going to derive the equations. So what is stable? Statically stable means dCm by d alpha should be less than 0. This is statically stable. Statically stable. If dCm by d alpha is greater than 0, this is statically unstable. If dCm by d alpha equals to 0, this is neutrally stable. Neutrally stable. For any lifting surface, if CG point is forward to my AC point, that is statically stable. For any lifting surface, if CG point is behind my AC point, that is statically unstable. And this neutrally stable I will tell you later, I will explain later once I derive the equations. Of course, in this condition, what is the neutral point? If CG and AC are at the same location, am I right? In this condition, if CG point and AC point are at the same location, are the same points, then here it is neutrally stable. Am I right? Consider, this is the CG point and this is the AC point. Both are at the same point. If there is change in angle of attack, increase in angle, now this is the equilibrium position. Oh, you are not able to see. Okay, I will write here. See, consider the only wing. This is the CG point and this is the AC point. Both are at the same point. Now, initially CMCG equals to 0. Means this is equilibrium position. If there is an increase in angle of attack, of course lift increases because of increase in angle of attack delta alpha. But what about the moment? Moment 0 only, because at the same point, what is moment? Lift is equal to lift into distance say x, but what is x here? Distance 0 only. So this is the condition, neutral is stable when I consider only wing configuration. Just I am giving example. Okay, now we are going to solve the derivation for longitudinal static stability. What is this longitudinal static stability? First of all, disturbance might be on any axis. Sorry, consider an airplane like this. Okay, it's not good. Okay, this is an airplane. This is one axis and this is along the wing, y axis, this is x axis, this is z axis, perpendicular axis, z axis, this is y axis. Okay, the motion or the rotation about the y axis is called longitudinal pitching moment. The moment, that is the motion, because what about the rotation that is about the y axis? Now the rotation about the y axis or the response of an aircraft to the disturbance about the y axis, that is called longitudinal static stability. Sorry, longitudinal stability means if I am dealing with this motion, the motion about the y axis, longitudinal static stability will come. If it is motion, rolling motion, means motion about the y axis, sorry, motion about the x axis, rotation about the x axis, then lateral stability will come. Their change in a pi angle, bank angle, I can say that bank angle. If I am dealing with beta, side slip angle or yaw angle, sometimes we can also say that yaw angle, both are different, that you will get to know. Yaw angle means rotation about this z axis, perpendicular axis, like this. If an aircraft, the motion like this, here you will have a picture of directional stability. Okay, now we'll study on longitudinal stability. Longitudinal stability is nothing but pitching moment. Here we are bothered about pitching moment, motion about the y axis, rotation about the y axis. Okay, there is a change in delta alpha, then what is the aircraft response, whether it is stable, unstable or neutrally stable. Okay, now we are going to derive the equation. Okay, consider a fuselage reference line first. What's this fuselage reference line? Name itself states that fuselage reference line. It's a reference line. It's in the mid of the fuselage. Okay, this is the fuselage reference line, mid of the fuselage, a straight line. Or you can also say that if you pass, I will write here. Mid of the fuselage means what? Consider an aircraft. If you consider a line like this, if you pass a vertical plane like this, if you pass a vertical plane like this aircraft is symmetric across this plane. This side also will get one wing, that side also will get one wing, same amount of for this side fuselage section, same amount of the fuselage section that side. Tail means the entire aircraft becomes symmetric across this plane. this is the mid. That's what I can say, mid of the aircraft or mid of the fuselage. So this straight line, a fuselage reference line is straight line that passes through the mid of the fuselage, that is called fuselage reference line. Okay, where I study light. Okay, here only I will write. That is called, now we are going to solve the derivation. Now we are going to not solve the, we are going to derive the equation for launch and static stability. So consider a fuselage reference line first. Okay, now I am going to consider wing first. We'll see wing contribution. I am not going to draw the entire wing. Instead I am going to write a chord line, chord of the wing. This is the AC of the wing. Okay, now this is called, this angle is called IW. What is this IW? Wing setting angle. In most of the cases, of course, this IW equals to 0, means the wing will be placed, if this is the fuselage reference line, of course the wing will be placed like this. But here I'm placing wing like this. If this is the body of the aircraft fuselage, I'm going to place the wing like this. I'm giving some wing setting angle just to derive for derivation purpose. That's it. Okay, now consider a velocity. This is the free stream. It makes alpha FRL with fuselage reference line. Then what is the angle of attack? Angle of attack will be alpha W. Na? What is angle of attack? Angle of attack is nothing but angle between the chord line and free stream. This is angle of attack, alpha W. Am I right? Then what is the lift? If this is velocity, the lift is always perpendicular to this. The lift is always perpendicular to this. This is the drag. Drag is always in the direction of the free stream. This is the drag. Now consider the one more axis here like this. These two axes are perpendicular, and I am going to place CG here. This is not the CG of the wing, this is the CG of the entire aircraft. Here I am going to show you the contribution of the wing. That's it. What is the contribution of the wing towards the stability? Okay, this is the CG point, CG of the entire aircraft. And from, just assume that this is the leading edge of the wing at this point. This is the leading edge of the wing. From leading edge of the wing to CG, this distance is XCG. From leading edge to AC, this is XAC. I am going to measure all the distances from the leading edge of the wing. Okay, now this is the drag, this is the force, and take this distance as XCG. Okay, now how do we write the moment? Moment is equal to force into perpendicular distance. So first we'll resolve these components, lift and drag. What's the lift of this component? What is this component? What is the angle here actually, first of all? What is the angle? See, these are the two axes. This is the fuselage reference line. Here I am writing you. Okay, this is the fuselage reference line. This is the perpendicular, what I have written here. Okay, what is this lift to force? This lift and this velocity, this lift and drag, or this lift and velocity, these two are also perpendicular. So first, what is this angle? Alpha W. What is this fuselage reference line? I want this angle. Okay, what is this alpha fuselage reference line actually here? alpha W minus psi W, alpha fuselage reference, this is nothing but alpha angle of attack minus wing setting angle. This is the angle actually, alpha W minus psi W, am I right? This is V, actually here this is velocity, this is lift. If this is alpha, what is this? If this is alpha W minus psi W, what is this? This is also alpha W minus psi W, am I right? Very simple. These two are perpendicular, okay, just assume that this is 1, this is 1, these two are also perpendicular. Now if I try to rotate this, if I try to rotate this, these two only, these two axes like this, if I try to rotate these two axes like this, these two are still perpendicular. If I give small displacement theta here, obviously it's also theta. Just I am rotating like this. Here also these two are perpendicular. If this is theta, this one also theta, because these two are also perpendicular, means this is alpha W minus wing setting angle, this is wing setting angle, this is also alpha W minus psi W, this is also wing setting angle, means what is this angle? Alpha W minus psi W. That's it. Now LW into what is the moment? Nose up moment, positive, and this is the AC point. Here I need to consider MAC. This is the moment at the aerodynamic center. This one also I need to consider. LW into cos of alpha minus IW, this is the component, vertical component, into this perpendicular force. What is this perpendicular force? From here to here, XCG minus XAC, XCG minus XAC, am I right? This is the force, this is the MCG, moment, this is the moment about to lift, XCG. Next, plus what is this dW? dW into what is this dW? It makes alpha dr means it will also make, see here what is this, alpha FRL. This is the straight line. If it makes alpha FRL, it also makes alpha FRL only. This is also alpha FRL, fuselage. Alpha FRL means alpha W minus IW. This angle is also alpha W minus IW. Okay, dW into, I want this force, perpendicular force. This is alpha W minus IW, means this is sine of alpha W minus IW. This is the component. If this is theta, this is sine theta. With respect to this axis, I want this component, vertical component, d alpha dW into sine of alpha W minus IW. What is the distance? Same, XCG minus XAC. This is vertical components done. Now consider horizontal components. What is the horizontal component? Same thing, LW. Of course, this is alpha W IW. This is L cos theta. This is L sin theta. L into LW into sine of alpha W minus IW. Go through this diagram, you will get to know everything. XCG, sorry, not XCG. This is the distance. If this is the component from this force to this, what is this distance? Perpendicular distance. I am taking it as a XCG. No, don't take it as XCG, you will be confused. Take it as ZCG, because I have taken XCG this time. From leading edge to center of gravity, this is ZCG. Okay, plus because of drag into cos of alpha W minus IW, ZCG. Got it? Just assume it. I am going to take the moment about the CG point, that's it. Here the lift component, two lift components will come along the vertical axis. I am going to resolve this lift and drag forces into two components along the fuselage reference line and perpendicular to that, vertical and axis, vertical and horizontal. So I am going to taking the moment about the CG point. Now what I need to find actually here, I need to find what is this dCG by d alpha, whether it is positive, negative or 0. That's what I want to know. Am I right? This is what I want to know. So if I want to make this CMCG, I want CMCG, I don't want MCG. What is moment equation? Moment equation is of rho v square s into c of rho v square s c cm. This is the equation. Now if you want to find cm, coefficient of moment, what should I do? mcg, this should be divided by of rho v square s sc. Make sure that when we are going to take moment about the cg point, if I want coefficient of the moment, I should divide it by half rho v square s into c. S is the surface area of the wing area. It should be wing area. It should not be tail area. It should be wing aerodynamic chord, not tail aerodynamic chord. If you want to find the contribution of the tail also, if you want to find the CMCG about the center of gravity due to tail, you should divide it by half rho v square sc. By this product only, you should take area, wing area and surface area and free stream. What is the free stream condition at the wing? Okay, you should be divided by, it should be divided by this only, whether it is due to tail or whether it is due to wing, whatever it may be. Okay, this is the cm, this is the coefficient of moment. Means if you want to get the coefficient of moment, you should divide it by half rho v square sc. So divide, you will get cm lw cos of alpha w minus iw xcg minus xac divided by half rho v square s into c plus dw sin of alpha w iw xcg minus xac divided by half rho v square s into c plus here also same thing divided by, just for your understanding purpose I am going to write each and every steps. This is not required actually, you guys can understand, you guys are smarter, I know. Am I right? I am going to divide this. What you will get? See here, what is this? L divided by half rho v square sc. What is lift? Lift can be written as half rho v square s into cl. Am I right? So L divided by half rho v square s can be written as cl. Means here L divided by half rho v square s, it will become cl divided by c. So this cm, same thing for cd also, this can be written as cl into cos of alpha w divided by iw into this xcg. Here divided by c will come, na? I am going to put it here, xcg xac divided by s. Am I right? I can write like this. Similarly for d also, drag, how do we write drag? Half rho v square s into cd, then cd can be written as drag divided by half rho v square s, it will become cd. So I am going to put it, I am going to substitute cd in this place. cd divided by c will come sin of alpha w divided by iw, this divided by cd I am going to put it here, xcg by c, xac by c. Similarly cl sin of alpha w iw into zcg by c plus cd into cos of alpha w iw zcg by c. Yes, that's it. This is the equation for the coefficient of moment. Now if you want to know dcm by d alpha, you should derive with respect to alpha, this cm, then you will get the contribution of the wing towards the stability. But this is the actual case, and this is the actual condition. but we are, in order to solve the solutions, in order to solve the problems, we are going to simplify it. Simplify means, actually this is the actual one. If you want to get perfect answer, you need to do this. You are going to derive, you are going to differentiate with respect to alpha, then only you will get what is the contribution of the wing. But in order to simplify it, what I'm going to do here means, in this condition, yeah, I'm going to do some assumptions actually here. This ZCG I'm going to consider it as approximately equals to 0, because this distance is very small compared to this distance, other arms. This distance is very close to fuselage reference only. The CG point is somewhat very close to fuselage reference only. So I'm going to take it as ZCG is approximately equals to 0, and this alpha W minus IW, it's also approximately equals to 0. Anyway, the angle of attack is, because the thing is, the angle of attack is very small. It is, of course, it's less than 15 degree, I think 15-16 degree like this. And in most of the cases, this I angle IW is 0. In most of the practical cases, the wing setting angle is 0. So I'm going to take it as sin cos. So what is, if maximum 15 degree means, if alpha angle of attack, what is sin 15 cos 15? You will cos 15, you will get almost 1. Sin 15, almost you will get near to 0. So I'm going to take it as approximately equals to 0. And the CL by CD, of course, it is greater than 1. Means it's actually, it's greater means CD is very less than CL when compared to CL. CD is very small. So I'm going to consider CD is also 0 approximately. I'm not telling it is 0, just assume that. So if with this assumption, if I'm going to write this equation, what CM will come? CM equals to, if it is 0, cos alpha, so alpha W minus IW, if it is equals to 0, cos 0 equals to 1, you will get CL XCG by C minus XAC by C plus sin alpha. If it is 0, sin 0 equals to 0, this term will become 0. Here CL, again it will be, and one more term I forgot here. I should take MAC also, na? If I take MAC, that will become MAC. That is the moment about this MAC. Sorry guys, I forgot this. I should add this one also. Sorry. Moment about the aerodynamic center. I should consider this one also. There is always some moment about the aerodynamic center. If it is cambered aerofoil, this moment is negative. This moment about the aerodynamic center is negative. If it is symmetric, it is 0. Okay. Sorry, I forgot to add that. Now XCG by C, XAC by C. Okay. Here, if it is 0, again it will become 0. Sin 0, approximately 0. And CD, here it is, but CD ZCG is also 0. It will also become 0 plus CMAC. This is the approximate equation we'll get for CM. Now, here one more thing. If you are going to derive this equation, dou CM by with respect to alpha, CL is a function of the alpha, of course, dou CL by dou alpha plus XCG by C, XAC by C. Of course, it is independent of the angle of attack. What is dou CMAC by dou alpha? 0. It is moment about the aerodynamic center. That is the definition of the aerodynamic center. It will become 0. So this is the condition. Of course, it's always positive. It's always positive. Dou CL by dou alpha, it's always positive. XCG by AC, XCG means if XCG is greater than XAC. In this condition, of course, XCG is greater than XAC. This XCG, I am placing XCG behind this, behind the AC point. So it is positive. It will become positive. If I place CG point behind the AC point, if I place CG point behind the AC point, it will become positive, and dou CM by dou alpha is greater than 0, means unstable, statically unstable. If I place this CG point, ahead of the AC point, if I place this CG point ahead of the AC point, then this term will become negative. Am I right? This term will become negative. If this term will become negative, of course this is positive, the entire term will become negative. Means dou Cm by dou alpha is less than 0. It will become negative. Now it is statically stable. Okay, this is the contribution of the wing. This is the contribution of the wing. Similarly, we are going to solve contribution of the tail also, but not in this section, in the next section. And but one more thing I want to add here, as a designer you should know this. If you want to make an aircraft, stable, what I should do? Of course, for any lifting surface, I should place the CG point forward to my AC point. This is what we have learnt in the last derivation actually. What's the contribution of the wing? If CG point is forward to AC point, of course it's positive, means it is stable. If its CG point is behind AC point, it's unstable. So here, if I want to make any lifting surface, stabilizing surface, I should place CG point forward to my AC point. Okay, now consider the entire wing now. Consider the entire aircraft. Here wing will come. Just this is the wing. Consider tail. Now where I can place my CG point in order to make my aircraft stable? Where? If I keep the CG point here, wing, it will generate destabilizing moment, because here is the AC point of the wing, here is the AC point of the tail. If I place CG point here, of course, now CG point it's behind the aerodynamic center of the wing. So wing, it will generate destabilizing effect. For any increase in angle of attack, alpha increases, it creates the destabilizing moment. But what about the tail? Now CG point is forward to my AC point. Now it will create the stabilizing effect. This is case 1. Here tail will give stabilizing effect, wing will give destabilizing effect. Consider the case 2. Wing, tail. If I place CG point, CG of the entire aircraft, if I place CG point forward to wing aerodynamic center, see here CG is forward to wing aerodynamic center, it's also ahead of the tail aerodynamic center. Here both will generate the stabilizing effect. Am I right? This is also stable. This aircraft is also stable. Here I cannot say that this aircraft is stable. I cannot say that aircraft is also unstable, because it is producing stabilizing effect, destabilizing effect, but tail is producing stabilizing effect. But whether this aircraft is stable or unstable, how can I say that? If I want to say that, I should know this configuration, this distance, what is the moment arm, this moment arm, and wing surface area, angle of attack, wing, tail setting angle, wing setting angle, wing surface area, everything will come. What is the lift that is generated for a change in angle of attack, and what is the lift that is generated by the tail, and what is the distance from tail aerodynamic center to the CG, what is the distance from wing aerodynamic center to CG, everything matters a lot. This is the moment. Moment is nothing but force into lift. So we should focus on force, lift into force into distance or moment arm and to distance x. Am I right? So here I cannot say that if this contribution is, in this condition, if this contribution is greater than this wing's contribution, obviously it is stable. If wing contribution is more than the tail contribution, then it is unstable. That's it. But in this condition, it is stable. Okay. But as a designer, can we prefer this configuration here? Can we prefer this configuration? I will tell you one thing. An aircraft should be stable. The graph should be like this. Means dCm by d alpha should be less than 0. dCm by d alpha should be less than 0. This is the graph. Am I right? For a stable aircraft. In this case, if I am going to draw a graph Cm, Cm versus alpha. See, at alpha is equal to 0, what is the moment that is generated here? If it is cambered aerofoil, of course there is always, even at alpha is equal to 0 also, there is always some lift, positive lift. If it is cambered aerofoil, that will create the negative moment, and there is always aerodynamic moment about the aerodynamic center. This is also nose down moment, so negative moment. And if cambered aerofoil, if usually the tail will be symmetric cross section, it will not generate any lift. Of course there might be some downwash effect. I will tell you what is this downwash angle. Because of this, there might be little bit lift might be generated here, but that is negligible. Am I right? That is negligible. When alpha is equal to 0, this zeta is very small, that too in case of only cambered aerofoil. Okay, because of this interaction, even though if alpha is equal to 0, here alpha might not be 0. In case if it is cambered aerofoil, there might be, because of this downwash, there is a zeta angle will be generated, and because of this there might be somewhat lift will be generated, very less. It is negligible. So in this case, at alpha is equal to 0, when alpha is equal to 0, CMAC lift, negative moment will be generated. Means at alpha is equal to 0, moment will be negative, and graph should be like this. First, of course, this is stable aircraft, then it will come like this. This is the graph. Am I right? Understand easily. When alpha is equal to 0, in this condition, if I place CG point ahead of wing aerodynamic center and tail aerodynamic center, this will create the negative moment at alpha is. What is the moment at alpha is equal to 0? Of course, if this is cambered aerofoil, this will also generate some negative moment. If this is, there is also a moment about the aerodynamic center, this is also nose down, so negative moment will be generated. Because of this wing, the moment will be generated, it is very less, even though it's very less. Okay, very less means it will come like this, or even though somewhat lift will be generated in the positive direction or in the negative direction because of negative angle of attack, like this. There is a negative zeta at alpha is equal to 0. There might be some positive moment that it will be like this. Just assume that, like this, or very less. So in this condition, take this is the graph. So here, what is the trim angle of attack? What is the trim angle of attack? Negative. Trim angle of attack is negative. So if you want to trim this aircraft, this configuration, you need to trim the aircraft at negative angle of attack. Means only when you trim the aircraft at negative angle of attack, only at this condition you will get CMCG equals to 0. So this is not at all possible. You cannot move like this, you cannot travel in, am I right? You cannot make aircraft fly like this at negative angle of attack. At negative angle of attack, what is it? The lift will be very negative. This is not possible only, this is practically impossible. So this configuration, as a designer, we cannot prefer this configuration. We should go for this configuration. But understand, if you want to make this aircraft stable, the contribution of the tail should be more than the contribution of the wing, because contribution of the wing is negative, means destabilizing effect. It will give destabilizing effect, it will give stabilizing effect. So the contribution of the tail should be more than the contribution of the wing. So next section we are going to study the contribution of the tail, and there you will understand all this zeta, wing setting angle, tail setting angle, etc. But make sure that I want graph at positive angle. I want to trim the aircraft at positive angle of attack. If I want to trim the aircraft at positive angle, this should be the graph like this. Means at alpha is equal to 0, what is the Cm naught? At alpha is equal to 0, Cm is taken as Cm naught. Cm naught is nothing but this is the moment of coefficient at alpha is equal to 0. So this should be positive. Am I right? This Cm naught should be positive. So this is the configuration I want. Understand? Thank you. It's already more than 50 minutes, I think. Thank you everyone.